So I hope you are all doing well. We are doing well here, Mr. Getz and I, and the kids keeping busy, keeping safe, keeping socially distant. I hope all of you are as well. So this would have been 2 days of material. I'm just going to make one PowerPoint. So the homework that went with it, there was a book assignment 5.5 with 2 questions, and then a handout with 4 circled problems, and that handout is on our classroom. So these 2 things go with section 5.5 in the book, which I know this is chapter 4, but we felt like this topic went with what we were doing, solving higher order differential equations. So this warm-up, if you want to pause the video and see if you can refresh your skills if you remember how to do this. Otherwise, I will go ahead and take you through it. They asked me to use the undetermined coefficients method. So remember, the first is to get the complementary solution, which is equal to 0. And I'm going to make this r squared minus 3r plus 2. Factors nicely, right, into r minus 2 and r minus 1. Therefore, I get r is equal to 1, r is equal to 2, which means my complementary solution looks like this. Right? And then to find the particular solution, right, to find y sub p by the UC method, we assume the solution takes on this form. Find the derivatives. Substitute in, back up here. Right, and hopefully you can see that these 2 will cancel out, and I'm left with 2a as the coefficient here is equal to 1, and therefore a is equal to 1/2. So then going back up here, y of p is equal to 1/2 e to the 3t. Which means that my overall solution y is equal to the linear combination of those. I'm going to do a little bit of foreshadowing here and tell you that this equation is going to come back sometime in this video. Okay? Sorry, it is a little, hopefully you can see that okay. All right. So again, remember that this was up here, this was a second order, And most of the examples I'm going to do today with our new method to solve differential equations is going to be second order, although it certainly works for higher order. The algebra just gets messier. Shocker, right? Okay. So Cauchy Euler. Cauchy was another French mathematician. His statue, I think, is in. There's a bunch of statues. If you ever visit France and go to Versailles, out in a courtyard, there's a big courtyard, and there's a bunch of statues of men. Unfortunately, I think there's a few women, all the way around, but they're pretty high, and there's a lot of mathematicians in there, from Descartes to I don't know, a bunch of people. See if you can, but I spent some time when I was there going around and finding my favorite mathematicians. Anyway, Cauchy, but obviously Euler, they were not contemporaries, right? But he's using Euler because really all we're doing is trying to guess and approximate some stuff for solutions. So the special thing about Cauchy, the Cauchy differential equations has to satisfy this condition here, where the power of the variable coefficients, right? Because we're not dealing with constant coefficients, we're dealing with variable coefficients, need to match the order of the derivative matched with that variable. So here's what that looks like mathematically. It still is a little confusing, but if you can see, these are derivatives right here. This is not y squared or anything, it's y to a derivative. So maybe that's, maybe let's say that's triple prime. So this might be x cubed, excuse me, then this would, in order to be a Cauchy differential equation, this would have to be y triple prime. And then this would be x squared, and this would be y double prime. And then this would be x to the first, and this is y to the first. And technically, this is x to the 0, and technically this is the 0 derivative, I guess, if you can think of that. And of course, this would be equal to either 0 if it was homogeneous, or equal to another function if it was non-homogeneous. So step one is to recognize that you can use the Cauchy, I hope I'm saying that right, Cauchy-Euler method. So first you got to look, right? You got to look and see if you can recognize it. And then there's one of two Cauchy methods, right? So that would have been the two separate lessons. I would have done method 1 one day and method 2 another day. And I'm just going to do it all in this one video. So since the first thing is to recognize, here's some examples of Cauchy-Euler. Can you tell? Let me take a moment to look at those. Well, this is pretty easy to recognize, right? Squared goes with y prime. X to the first here goes with y prime. And then, of course, we think of this as x to the 0 and the 0 derivative. This one, x cubed, y triple prime, x squared, y double prime. So the power cube matches the order of the derivative. But what's up with this third one? That's Cauchy in disguise. Can you tell why? This obviously doesn't match. But I have an equation. If I want to use Cauchy, what can I do? What if I multiply everybody by x? What do I get? Right? And now, check. So Cauchy, Cauchy, Cauchy in disguise. Right, and even if this was not 0, I could still do this, because every time that I go to solve, even if I solve a non-homogeneous, remember the first thing I do is solve the homogeneous, right? So I always set it equal to 0 and solve the homogeneous, the complementary function. All right, so recognize. So method 1. both of what Cauchy does is transform equations to match his form. So if I'm not in the Cauchy, right? I mean, once I'm in Cauchy Euler form, Cauchy's form, then I'm going to transform. And method 1 is this transformation. Method 2 will be a different transformation. So we're going to use the substitution that x is equal to e to the t, which, if I take the ln of both sides here, I get this, right? Or I undipsy-doodle this. Do you remember that if I had you for AAF, right? The exponent that turns e into x is t, right? So I'm going to do a proof and then we'll do an example. And the purpose of doing the proof is to get a formula so that I don't have to go through all the algebra steps each time I want to do a transformation. So that's the purpose of the proof. Right? It's kind of like the quadratic formula, right? The quadratic formula is a proof of, right, of solving the general quadratic equation using completing the square and blah, 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 and getting x by itself. But you don't want to do that every freaking time. You want to use the quadratic formula. So that's what our goal here is. So the first thing I'm going to do, since we are dealing with differential equations, I'm going to take that t equation and tell you that take its derivative. So I have dt with respect to x, and that is 1 over x, and of course we're going to talk about, we're going to leave the mandate the condition that x is greater than 0, which of course goes with the domain of ln, right? So there's a second order Cauchy equation. Do you see it? And it's non-homogeneous, given that f of x is equal to some function in terms of x. So remember, everything now is in terms of x. So this y double prime is, right, this is all over with respect to x. Y prime is with respect to x. This function over here is in terms of x. So I'm going to focus on the derivatives here, right? I have dy, you know, this is the y. I'm going to want to substitute in for y double prime, and I want to substitute in for y prime. And you might be tempted to say, well, you have a derivative over here with respect to x. But it's not dy, is it? It's dt. But I taught you calculus now, didn't I? So I am going to find y prime, the first derivative. And when I taught you calculus and when I taught you the chain rule, I taught you that the chain rule is also a product, right? It's a product, and here is the chain. Right? So there is, right, dy dt times dt dx. So that's the derivative of y with respect to x if I want to try to get the t's in here. Right? So where did that come from? Right? Do you see where this came from? Taking the derivative of y with respect to x, I get my 1 over x, because that is dt dx, right? But I want to, right, taking the derivative of 1 over x. Right? But I have to spit out using the chain rule, dy dt. Okay, you okay with where this comes from? dt dx. It's right there. So taking y prime with respect to x, given that I'm going to do a transformation here, where x is equal to e to the t, but t was equal to ln x, that way I could get my dt over dx. So I'm going to be able to substitute in for y prime. Now what am I after? Right, I didn't do anything here. I just copied this over. Now I'm going to go try to get the second derivative. Now be careful, right? I'm taking the second derivative of a product. I'm taking the derivative of a product, right? So take the derivative of the derivative, but the derivative is itself a product, so I have to use the product rule. So to use the product rule, right, the second derivative is the first function, 1 over x, times the derivative of dy dt. So what is the derivative of dy dt? But remember, I am taking derivatives with respect to x. So that is whatever, right? So you have to take the second derivative. That's where this comes from. But you have to spit out the derivative with respect to x. The derivative, since you're doing your t, dt over dx. Right? So first times the derivative of the second. Then what the heck is this? Why is there a minus? This is supposed to be a plus, right? That's because it is plus the second function, dy over dt, times the derivative of the first. But what's the derivative of 1 over x? And that's where this term comes from. I'm going to put in 1 over x there for dt over dx. And I clean stuff up a little bit, and then right, so I just replace this right here. And then can you see what happens here? Right, 1 over x times 1 over x is 1 over x squared, which is also here, so good F word. Right, factor it out front, and now I have the second derivative. Right, I was after the second derivative, and there it is. So I now have a box for the first derivative, a green box, and I have a green box for the second derivative. Box 2, box 1. Okay? All right, now what? Oh, by the way, I could keep going, right? If I was doing higher order, I could do the third derivative. It starts to get a little ugly, right? And certainly then you can see the fourth derivative, and that's why sometimes people prefer using the second method especially if you're going beyond the second derivative. This isn't so bad, especially if you really do just have to remember your boxes. And further, I'm going to show you I could stop here and say just remember your boxes, but let me go a little bit further. Say I'm going to substitute now for the derivatives, right? These are my boxes. I found y prime. I'm sorry, I just didn't do that in order. I said find y prime, that's box 1. And I found y double prime, which is box 2. Don't forget though, you're doing a transformation. I haven't done the transformation yet. Right? I'm just replacing. I've still got x's in here, but remember this was all built on the fact that we were transforming x into e to the t, which is where we got the t is equal to ln x, and we use those derivatives, right? So I've got t's in here and x's. That can't stay, right? I was all in x's, but now I've started to introduce t with the chain rule, and I replaced y double prime and y prime. But now I have to finish the transformation by putting in x is equal to e to the t. So I'm going to have to put e to the t here, and square it, e to the t here, and I hope you see what happens, right? And you might be thinking to yourself, well, why would you do that? Why not just cancel them out there? Well, you have to be very careful because there's some place else that I have an x that I have to transform to make this all legal. Do you see it? Yeah, over here, right? Hello. I've still got some x stuff over here. So if you just cancel these x's as if you didn't make the transformation and then leave this function, you're going to be in trouble. So maybe you just mentally do this part, right? And that is e to the 2t, right? But those are going to go away, just like the x squareds would go away. These are going to go away, just like the x's were going to go away. But be careful, this isn't f of x anymore. You have to substitute e to the t for x. So that simplification means I look like this. Now I want you to see if I can I'm going to do a little algebra 1 here. And I highlighted and made bold the coefficients. Right? You see what I did there? So I distributed the a sub 0 through there. But now if you notice, what do I have here? I've got 2 of those. So again, good F word. Look at what I did with factoring. So now notice, this isn't, I mean, I can use this notation. This is y double prime, and this is y prime, but it's not with respect to x anymore. Who is it with respect to? Right? So, if I have a Cauchy-Euler equation and I recognize it, I can skip all of that proof stuff and recognize that I'm always going to end up with an equation where my leading coefficient is the leading coefficient I started with. That's going to be in front of y double prime, right? But what's going to be in front of y prime, that coefficient is the coefficient that was in front of y prime minus the coefficient that was in front of y double prime, and that just came from algebra. Nothing happened to the next one. And then, of course, remember that what your equation is equal to has to be in terms of t, and it came from your original function where you replaced x with e of t. That is Cauchy's equation. So this is what I call the formula that we ended up with. So you can either remember this, or you can just remember what your 2 boxes were. So I call the box method and the formula method. And I guess I shouldn't say method, formula way or box way, because that's not the 2 methods I referred to at the beginning. This Cauchy-Euler transformation is with e to the t. So let's do an example. Oh, after I'm done this transformation, then I would keep going. If I was only doing a homogeneous equation, I would be, I could be just about done here. If it was non-homogeneous, I'd have to use undetermined coefficients or the method of variation of parameters. But look at what I have here, right? There's still this something that has to be done. See if we can figure out what that is when we do an example. All right, so example 1. Is this Cauchy or Cauchy in disguise? This is just a Cauchy, right? It is non-homogeneous. So I'm going to do this problem by my formula. Can you tell what we need to do here? Right? The transformation will have the coefficient of y double prime 1, the coefficient of y prime be -3, and the coefficient of y is going to be 2, and my function on the other side is going to be e to the 3t. Well now. Hey! Oh snap! Isn't that what you did in the warm-up? Right? Didn't we already do this? Right? That's called planning. So remember, when we were, right, we turned this into r squared minus 3r plus 2 is equal to 0, and blah, 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 blah. So we got that equation. Now, we're still not quite done, but I wanted to show you that we don't have to do this math because you did it in the warm-up, but I wanted to show you if you didn't like the by formula method, if you didn't want to do this, some people prefer to use what I call the box way. And the box way means instead of remembering this formula, you just go up here. Well, I'm sorry, you memorize these formulas, right? That x squared, without its coefficient, x squared y double prime is always going to be this box, xy prime is always going to be this box, and then of course your function on the right side is always going to have e to the t in it. And then they go back to the original and substitute. And when you substitute box for box, you end up with that equation, but again, look what happens right here. Right? You end up with this -3 still. And then of course you have the same non-homogeneous differential equation from the warm-up, which we solved in t. But what was the very first thing we did? That was our answer from the warm-up after we solved, right, after we combined the complementary and the y sub p, right? We got a to be a half. But this is where the and then comes apart from. You can't forget that x, we transformed x to be equal to negative e to the t, so we've got to put that back. So what does that look like? Well, this is just going to be x, right? What's this going to be? Yeah, and how about this? Nicely done. Thanks, Cauchy. Right? So this is where you might want to fill in the then ... right? Retransform, I guess, it's a way to make that up, make up a made-up word. So the two book problems that you have to do for homework from section 5.5, both of them you should practice this method on. And one is homogeneous and one is not homogeneous. But they're both, I think, fairly straightforward, and you'll be able to follow from these examples, from the example that I took you through, the proof and the example. All right, so that's where we would have ended had this been a normal class, and then the next slide would have been the warm-up for the next day. But we're going to make it our second example. So again, if you want to pause here and try this on your own using the first Cauchy method, where your transformation is going to be e to the t, and you can do the box way or the formula way. Okay, I'm going to go ahead and do this by formula, where I do recognize that I've got Cauchy, right? So, yay. I'm just going to go ahead and make this, right? Consider this homogeneous. Right now, I'm going to do the complementary, where I'm going to take x squared. Well, no, I'm not. I'm going to go ahead and make this. I'm going to do the transformation for it all, right? I'm going to be putting So what do I have? Okay, so there's my transformation. Now I'm going to find my complementary. And my complementary solution using my formula, I'm going to say, since I had Cauchy, A A sub 0 is this coefficient here, right? 1. And A sub 2 is this coefficient, 4. But what is A sub 1? Right, A sub 1 is not just here, right? It's negative 4 minus 1. Truth? Right, are you okay with that? So, when I'm solving for y sub c, the complementary, so equal to 0, I just have 1 r squared minus what? 5r plus 4 is equal to, and I'm taking this part, right, or this part, whichever you want to consider, and making it, since I'm doing the homogeneous one first, making this equal to 0. Good. Now I can actually make a decision at this point. While I want to, if I want to retransform here, right? But if I retransform here when I'm doing y sub p, I'm going to be dealing with a cubic. Right? And if I use my undetermined coefficient, I don't think so. So I think I'm just going to consider that I'm still in t. So I'm going to go from here and say y sub p is equal to what? A e to the 2t and b e to the 3t. And then take the first derivative. The second derivative. Substitute in. Right, x squared. Are you okay if I skip that? Sorry, I'm going here, right? right? That's really from here. Yeah, I have my e's, blah, 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 but I don't really care because I'm trying to match these guys, right? So what do I want? I want my e to the 2t's. So I have 4a and what? Negative 10a, and then plus 4a, and that's all going to equal 4. And then (9b) and negative 15b and 4b is all going to be equal to negative 6. Whoops, 4a, not 8. So negative 2 is equal to 4, meaning a is equal to negative 2. And then, what did I say for b? My gray ones are 9b minus 15b equals negative 6. So I got negative 2b again is equal to negative 6. I got b is equal to 3. So that means y sub p from up here was negative 2 e to the 2t and 3 e to the 3t. So therefore, y was equal to what? Oh snap, what did you forget to do? Right, let's put back x, right? So yc is actually c1 x to the 4th, c2 x, and here we have negative 2 x squared and 3 x cubed. So my final y is c1 x to the 4th plus c2 x to the 1st minus 2x squared and 3x cubed. Ta-da! All right. So again, that was method 1. With the transformation x is equal to e to the t. So what is method T? Method 2. What could method 2 be like? Well, this time we're going to use the substitution y is still in terms of x, right? So instead of introducing t, we are going to keep our x, but we're going to make y x to the r, and we're still going to use the condition that x is greater than 0. And it is the most common one, so there is a process for when x is negative, and you can look that up, but we are not going to consider that in our course. So here's my Cauchy-Euler equation, right? Do you recognize it? Because that's always step one, is look to make sure. So I have a second degree, second order, first degree, first order. So step one is to take the derivative of y, right? If y is equal to x to the r, I'm going to take the derivative of y with respect to x, so I don't have to worry about this resubstitution. Oh, so, and notice that also I made this homogeneous. It doesn't matter if it is non-homogeneous. I don't have to worry about transforming it since I'm keeping with respect to x. And the step one in non-homogeneous is to consider the homogeneous case first, right? So this is just my power down rule. And then I just power down again. And then I'm going to stick with the second order, but you can imagine that here for the second derivative, right, what I would have. I would have r minus 1 times r minus 2, x to the r minus 3, and I could keep going. So the algebra does get nastier, but at least you're not taking those derivatives like you were in method 1 that were so nasty with the chain rule and making sure you get t involved and, you know, chain. Here it does get algebraically messy, but it's not, I don't have as much to keep track of. I just have to keep track of the power down rule because I'm not transforming x into another variable. So, but I'm going to stop here, and I'm now going to substitute in the two derivatives I found. So I'm going to substitute into this equation for y prime and for y double prime, and I'm going to put y in here. Okay, so that's what that looks like. Oh, see, this is where I need some art, right? This is up in exponential land, and it's not supposed to be, right? This is supposed to be down in normal land. Okay. Now I'm going to simplify this a little bit, and I know that I could make that r squared minus r, but I'm not gonna just for a minute. So, do you see what happened here? Something cool happened with these exponents, right? If I have x squared, and that is being multiplied eventually times x to the r minus 2, what does that turn into? Which is just x to the r. Oh snap. And then look what happens here. This is x to the first, which eventually is going to be multiplied by x to the r minus 1, and look what that turns into. Oh snap. And then this was already here. Whoa! So I can factor that out or divide it off. Regardless, bye-bye. And look what I have here. If I, right, this looks familiar. If I go ahead and distribute that, I have r squared minus r to the first, both with an a sub 0, right? Plus a sub 1 to the r, times r, excuse me, plus a sub 2. So what did I do here? Well, this looks familiar. Wait a second. Not only does that look familiar from what I did before, but hold the phone. This is just a regular what? Quadratic, right? Whoa! This is a quadratic equation, And the quadratic equation, remember we made x greater than 0, has either 2 real, 2 repeated, or 2 complex roots. Say what? And then if you remember all the way back to, what was it, chapter 3, we know what to do with this, right? 2 real, for 2 real, and again, if this was higher order, it would just be, more of them, but how do I get these 2? I either factor or use the quadratic formula, or divide if it's higher order. Factor, quadratic formula, divide, same thing, right? If it's repeated, do you remember what we had to do for repeated roots in order to make sure that we had linear independence? Do you remember that? We had to multiply the second factor by x, right? Well, now I've already got an x, and as a matter of fact, I usually have an x to the r somewhere. Instead of multiplying that by x, I need to multiply it by, wait for it, not x, but ln x. Naturally. And of course you have to have your coefficients, right? You'll have your coefficients here. How about 2 complex roots, right? Do you remember we had a plus or minus bi and what that ended up looking like with the mauve? Remember that? Well, here what we're going to do now, we're still going to have, and again we're going to have our x to the r. I'll put the coefficients in this time. Yep, this is going to be cosine. And this is going to be sine. But in there, and I should have made this red, shouldn't I have? This is going to be b ln x. This is going to be b ln x. Naturally. And that just comes from some proofs and transformations. Now, you are only going to, in homework, you're only going to have to deal with this. One of the equations, or I'm sorry, one of the problems from the worksheet, not the textbook, from the worksheet, you will end up with a 3rd degree, but you can divide and get all 3 of them. You do not have any examples of repeated or complex to practice. I just wanted to give you that information. Oh, one of the problems, though, is an initial value problem where you actually are given enough information to solve for your coefficients. All right. So again, I could keep going. So this information you might need for, right? This is what you'll need for one of the problems. As you can see, I just end up with a r minus 1 and an r minus 2 here, right? Oh, that's not right. I have to do this. Well, you'll figure it out. So step 6, though, remember you had the complementary solution. You need to put with the transformation, just like before, you have to put the transformation back. It's just a little easier. The r's that you find are actually coefficients on x. Right? And then if it's homogeneous, you stop. If it is non-homogeneous, you go on to use the undetermined coefficient or variation of parameters method. You're like, whoa, it just happened. Oh, my Lanza. All right, so let's do an example, but we're going to do an example of a problem we've already done. Right, so we did this with the transformation, right, with method 1. And we did the transformation where x was equal to e to the t. But this time, I'm going to use the transformation where y is equal to x to the r. So I replaced y. I replaced y prime. And I replaced y double prime. I lost an x there, didn't I? Thank you, Samarth. And I just replaced the, so I don't have to worry about transforming this, right? Because I'm staying in x. So right now I'm going for the complementary. So I went ahead and made this 0. Right? And remember, this x squared multiplied with this x to the r minus 2 just left me with an x to the r. This x to the first times this x to the r minus 1 left me with just r to the first. And then this was 2x to the r. And then I divided everybody by that x to the r, or factored it out front, if you will, and then, right? Which then gets me down to r squared minus 3. Remember where that came from? That came from this r squared and this r, and then this is minus 2r. So that's where I end up with the minus 3r. And then I'm going to factor r minus 1 times r minus 2 is what I get. So don't forget, what do those r's turn out to be? Those r's that I solved with that quadratic actually are exponents coming from y is equal to x to the r. So I just put the 1 and the 2 there. Good. What's my next step then? Since this was not homogeneous, I now have to go and try to solve, right, and take care of this. So y sub p is equal to a, and again I should do plus bx squared plus cx, right, but I think you can figure out those all will end up being 0. So I trust you'll be able to do this math and get that a was equal to 1/2, right? So you might want to practice that. And then shocker, what do I get? Same answer I had before. Woot woot, woot woot, woot woot. All right, so thank you very much for staying with me with all of this, and I will talk to you later.